Finish up with the factors that affect air pressure, and then hopefully move on to a little bit more of sea breeze and land breeze. Why is it? Oh, there we go. Okay. So yesterday we determined that as altitude increases, air pressure decreases. All right. And you can see this in your ESRTs, right? On page, what is it, 14? No. Sorry. Yep, page 14. All right. So if we look at page 14 in our ESRTs, whoopsie. All right. As we move up in altitude, as we get higher and higher and higher in altitude, if we look at this pressure graph, at sea level, the air pressure is 1 atmosphere, right? There's 1 atmosphere of air on top of us right now. But let's say we went up to 10 miles above Earth's surface, or even 5 miles above Earth's surface, right? That's about the height where planes fly, right? 25 to 35,000 feet. If we go across, we're still in the troposphere, right below the tropopause, but look what's happened to the pressure. If we go straight down, it's about 0.2 atmospheres. So as altitude increases, air pressure decreases. This is what kind of relationship? This is an inverse relationship. So if we just make a little graph here, right? So altitude is our independent variable, and we're at a low altitude or a high altitude, and air pressure is our dependent variable. We're at a low air pressure or high air pressure. If our altitude is low, we're closer to Earth's surface. Air pressure is higher. James, you're not going to get anywhere with sitting there with your arms folded. You should be writing. If I'm writing, you're writing. But if we're at a high altitude, like if we're on the top of Mount Everest, or like if we're in an airplane, that would be low air pressure, and that's what the relationship looks like. All right? So that's the first factor that affects air pressure. And that's just, the air is just on top of you. How much air is on top of you? All right? Now, then we started talking about temperature. How does temperature affect air pressure? All right? So we really have to think about density. We're going to be applying density a lot. All right? If we think about warm air, right? Warm air's molecules are very, very, very far apart. This is warm air. Okay? What about cold air molecules? What about their distance away from each other? Cold air molecules are closer together because it's denser. If we think about a certain volume of air, in that same volume of air, cold air has more molecules in it. So that, think about the weight of that cold air pushing down on you, right? This pushes down on you harder than the warm air, because it just weighs more. It's more dense. Cold air is much more dense. So if we think about the graphical relationship, and we think about the temperature of the air, if the air is cold or if the air is warm, and we think about air pressure, now this is just air that's hanging out on top of you, like it's not moving up or down, because we're going to get into that soon. What if air moves up or down on top of you? That affects air pressure too, right? But cold air, much more dense. How is that going to affect the pressure? It's more dense, pushing on you. Well, I already said the air is cold. It's more dense. How does that affect air pressure, Noah?
It would make it low. No.
It's pushing down on you. Think about what's pushing down on you, right?
Higher.
It's heavier, right? It's pushing down on you more. So if it's cold air, it's much higher pressure. The air weighs more, right? Okay. And then if the air is warmer, it doesn't weigh as much, so it's not pushing on you as hard. That's lower air pressure. So what kind of relationship is that? That's an inverse or indirect relationship. So as temperature increases, air pressure decreases. And this is A or N, inverse, or what we call an indirect relationship. All right? So this temperature is really about the density, okay, the density of the air. Altitude is really about how much air is on top of you when you're at different altitudes in the atmosphere. All right, so here is the information about cold air and room temperature air and warm air. Okay, we have a certain volume of air, the same volume in all three places, right? Here, the air molecules are very, very close together. Why are they so close together? Because they're not moving as much. They have less thermal energy. Okay, here we increase the mass. We increase the temperature. Okay. They're moving a lot faster. What happened to the amount of air molecules that were in the parcel of air? It decreased because they're bouncing off each other so hard. Is this ringing a bell? There's more space between them. What if the air is really warm? Here we have a lot of air molecules. Here there are fewer air molecules. What should we draw here? Even fewer. So we have, let's see, 1, 2, 3, 4, 5, 6, 7, 8 here. Maybe in the warm air we'll draw 5. And how should we represent that the air is warmer than the room temperature air? What are we going to do to represent? Longer arrows, showing that these molecules have way more movement because they have way more thermal energy. Okay, so here the density, let's call it high density. We'll call this mid density, and we'll call this low density. All right, so here, since it's high density, let's make a really bold arrow. It weighs more pressure. Here, let's make the arrow smaller. It weighs less. That means less pressure. Here, let's make the arrow the smallest. It weighs the least. There's the least pressure. Okay? So that's basically how the temperature of the air above you affects the air pressure. Those two factors, they kind of make sense, right? Hey, it's all about the weight. It's all about the weight of the air above you. They make sense. The third factor is counterintuitive. Let's think about those dog days of summer, those really hazy, hot, and humid days of summer. Let's think about them. How does the air feel when it's really hazy, hot, and humid? How does it feel? No? It feels heavy, doesn't it? It's like, it's like on you, it's sticky, it feels heavy, right? Let's determine the reality of the situation. What we're going to do is we are going to actually calculate the mass of dry air, and we're going to calculate the mass of humid air on a molecular level, on an atomic level. And we're actually going to determine, is humid air more heavy? Right? Heavier, I should say, right? Okay. So if you think about humid air, why is it so humid? What's in it? Water vapor, right? And doesn't water weigh a lot more than air? I mean, think about carrying a gallon of water. I'll carry a gallon of air before I carry a gallon of water any day. But is it heavier? Let's figure it out. All right? You're going to need a pencil because we're going to draw. And you have your calculators ready? Calculators ready. Okay. All right. We're going to use circles to represent each type of molecule or atom that is found in air. Now, what are the big 5? Nitrogen, which is N2, okay? Oxygen, which is O2, water vapor, which is H2O, carbon dioxide, which is CO2, and argon, which is just AR. Okay, it's just a single atom. The rest of these are molecules. We will put a total of 17 molecules or atoms in each parcel of air. Remember that when a molecule of a substance enters the parcel, a different molecule is going to get the boot, or it's going to get pushed out of the parcel. Okay? Remember that each box of air must have an equal amount of total atoms of molecules, which is 17 each. Okay? So we're going to draw some dry air over land. Now, what we're in, where are we? We're in the desert. Let me write that a little bit bolder. This is the desert. Now, even when you're in the desert, the air does contain a wee bit of moisture. It's not completely 100% dry, all right? So the first thing that we're going to do is we're going to draw 17 circles. We're going to spread them out. So you need to make them about yay big, okay? So just draw them randomly. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Let me just make sure. 1, 2, 3. Yep, 17. I got 17. Okay? Now, the majority of these air molecules is what gas? What's the majority of the atmosphere made of? Nitrogen. So let's make 10 of them N2. So just, you're going to write N2 in 10 of them. Spread them out. Okay. That's 10. So, what we're going to do down here is we're going to calculate how much that N2 weighs. So we have N2. How many of them did we draw? And then we're going to figure out how much they weigh in a second. Okay? What's the next most common gas in the atmosphere? Jake. Oxygen. Let's make 4 of them oxygen. Okay, so O2, 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 O2. So for oxygen, how many of those 17 molecules did we make oxygen? 4. Right? Now we have 3 molecules left. We're going to make one of them H2O. We're going to make one of them CO2. And we're going to make one of them argon. So H2O, 1, CO2, 1, and argon, 1. So now this count is the number of either molecules or atoms in the parcel. In reality, there's trillions, right? But we're just making a model, all right? So now, what do each one of these molecules or atoms weigh? Well, if you remember from the periodic table, the atomic mass is the number of protons and neutrons in the atom, all right? And the atomic masses are listed right here. What is the mass of one nitrogen atom? 14. Okay, one atom of nitrogen has a mass of 14. But we don't have one atom of nitrogen. What do we have?
10.
We have no, we have a molecule of nitrogen. Is that okay? We don't have N. We have N2. So we don't have this. We have that. Is that okay? We have a molecule of nitrogen, which consists of how many atoms? 2. It's like a barbell of nitrogen. Is that okay? So N2 doesn't weigh 14. What does N2 weigh? 28. You got it. So we're doing 10 times 28 AMU, which is atomic mass unit. So what does all that nitrogen weigh? 280 AMU. Is that okay? Do you want me to explain that again? Yes, no? We're going to do it again, so it should make sense in a second. Okay. One oxygen, how much mass does it have? 16. An atom of oxygen has a mass of 16, but we don't have an atom of oxygen. We have 2 atoms of oxygen. O2, right? We have a barbell of oxygen, right? So we're not going to do 4 times 16. We're going to do 4 times 32 AMU. And what's 4 times 32? It's 128 AMUs. So that's the mass of all the oxygens. Okay. Now, H2O. What is one atom of hydrogen mass out at? 1. But we don't have H, we have H2. So this hydrogen has a mass of 2. And oxygen has a mass of 16. So this is 16. So H2O has a total mass of 18. So 1 times 18 is 18. Okay. We're going to do the same thing for CO2. 1 carbon has a mass of 12. And 2 oxygens, we already figured out, has a mass of 32. So what's 32 plus 12, everybody? 44 AMU. And there's 1 of them, so that gives us, we're going to add 44 AMU. And finally, Mr. Argon. Argon has a mass of 40. We have 1 of them, so that's 1 times 40. And that's 40. Let's go to camp, add them up. What do we get? 510? Does everyone agree? Do we have consensus on that? It's always good to have a check, right? Is that okay? Okay. So this is the mass or weight of dry air. That's the mass or weight of some dry air, a sample of dry air that's hanging out over the desert. Now let's say this is the desert of Mexico. All right? And this dry air over the desert of Mexico is going to move. It's going to move over water. Where would dry air over the desert of Mexico move to? How about the Gulf of Mexico? Yeah, how about the Gulf of Mexico? Now, the Gulf of Mexico is very warm. Yeah? So, because it's very warm, what's going to happen off of the water? A lot of what? Yes. A lot of evap. Whenever I draw the squiggly line, whenever I draw a squiggly line coming off of water, what process does that represent? Evaporation. So now, this water that's in the liquid phase will evaporate or evaporate into water vapor. And every time a molecule of water vapor goes into the parcel, another molecule that's already there is going to get booted out of the parcel. Because how many circles are we going to draw in this parcel? We're still going to draw 17, so make 17. Okay. We're going to increase the amount of water vapor first. Okay, so we're going to draw H2Os. Now we had 1 H2O over here. How many should we put over here? We'll do 4. We'll even make it mildly humid. Let's make 4, okay? So we'll make H2O, 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 and H2O. Okay, so we have 4. We had 1 H2O over here, and now we have 4. All right? So what we're going to do is we're going to list all of our molecules in the same order. So So we're going to have N2, we're going to have O2, we're going to have H2O, we're going to have CO2, and we're going to have argon. But now we don't have one. Now we have 4 H2Os. So something's got to give, yeah? Last time we had 10 nitrogens. I say we knock that down. We're going to knock it down to 8. Okay? So now we're going to have 8 nitrogens. So now we're going to draw 8 N2s up here. Okay, so we're gonna have 8. We'll knock the oxygens down to 3. We have 2 more blanks. We're gonna still make 1 CO2. Oops. And we're gonna make 1 argon. Is that okay? So we got 1 and 1. Did everyone fill up all 17? Okay, so what changed? We have more water vapor now. A couple of nitrogens got the boot, 1 oxygen got the boot. Is that okay? So do we have a total 8, 9, 10, 11, 12, 13, and 4, 17. So we still have 17, yeah? Let's redo our calculations. Everyone work on that. So we're just gonna steal it from here. We already figured out what each one mass is at, okay? Go to camp, add them up. Whoa, what'd you get for your total? 476 AMU. Whoa. Nola, does everyone agree with Nola what she said before? Like, doesn't humid air feel heavy? Is it heavy? No. So contrary to how humid air makes us feel, this is the mass or weight of humid air. It's also called moist air, but I know some people don't like that word. Wow. So actually, how does the humidity of the air affect air pressure? Think about it. It's all about the weight of the air above you. Got it. Yep. As the humidity increases, the air pressure decreases because humid air weighs less than dry air. Even if you have the same number of molecules above you, H2O molecules, water vapor, remember this is not liquid water, okay? I know, water's heavy, yeah, when it's a liquid, okay? Water vapor, not so much. We just proved it on an atomic level. So let's turn the page. How does humidity or the amount of water vapor held in a parcel of air affect air pressure? We just proved, and I've recorded this, page 8. We just proved that H2O molecules have less atomic mass than N2 and O2 molecules that they take the place of. We already proved it, yeah? Okay? So how does humidity or the amount of water vapor held in a parcel of air affect air pressure. As humidity increases, air pressure, yes. Contrary to how it feels, air pressure decrease. This is a what kind of relationship? This is an inverse or indirect relationship. Yep. Even though humid air feels gross and it feels heavy, it's actually not heavy. Go ahead, James. Why does it feel like that? It's just because of our senses and how it just feels to us. Our perception, because we're sweating and our clothes stick to us, it's just perception. That's it. It's just perception. We can't sense differences in mass on the atomic level. Do you know what I mean? And the only way that you would feel a difference in air pressure is probably if you have either migraine headaches or arthritis. Other than that, you're probably not going to feel in your body differences in air pressure. Does that make sense? All right. Okay. So you're going to be tackling that page tonight. Let's go to let's go to page 10. All right. Wind is the movement of air parallel to the ground. What do you think causes wind? What do you think? Write it, whatever you think, write it down.
I never got the convention.
What do you whatever you think causes wind? It's not right or wrong. Just write down whatever you think causes wind. What is some people thinking? What causes wind? Energy differences? Okay. Will? Convection currents. Okay. Yep.
I guess kind of like difference in density between the cold air.
Okay, density differences. Good. You're all thinking density diffs. Awesome. Henry? Okay, air pressure differences. Oh, you guys are kicking butt and taking names. This is awesome. Air pressure diffs. Yes. This leads to that. That leads to that and that. You actually listed them in order, so that's really good. Yeah. Okay. Let's review for a sec. The circular movements of air or any fluid, because fluids is matter that flows. Awesome. What is this thing called? Are called convection currents. Wind is caused by differences in density, temperature, and pressure. Yep. Okay. If this is a closed box and there's a candle over here, what would the convection current look like? This is where the air is getting heated. So what's happening?
The air moves to the right,
In outside the box or inside the box?
inside the box.
The air is going to move this way?
Or like up.
Oh, the air is going to move up. Okay, then what? What's going to happen? Is the box going to become a vacuum? If you had your pet mouse in here, would the mouse perish because it was running out of air? No. The air is definitely leaving here, but it's not going to create a vacuum in here. This matter needs to be replenished. Where is the matter going to come from to take this place? It's going to go in this way, isn't it? Yep. And then what's going to happen? How is it going to move? How is the air going to move in the box? To the right or to the left?
To the left.
To the left, to the left. You got it. Can you do the same thing down here? Except now the candle's on the right. Is this ringing a bell? Remember, as matter leaves an area because it's getting heated and rising, does other matter need to come in and take its place? Oh yeah, absolutely. Yep. And it's easier for the matter to get sucked across the bottom than fight the power, yes? You're not going to fight the current. This air is getting heated. It's becoming less dense and rising. The air molecules are leaving the box. What's the easiest way for new air molecules to come in and take their place? Right in there, and it's getting dragged across that way, yeah? That's the bottom of a convection current. If you're standing here and this is Earth's surface, what are you feeling? You're feeling wind. You got it. Wind is the lateral movement of air. You got it. Okay. Land heats up and cools down faster than water. Why? Jake? Land has a lower specific heat. Is that all you have to say? Than water, not then water, than water. That's the comparative then. Then is next. Than is comparison. Okay, there you go. Water has a really high specific heat. Okay, 2 p.m. on the beach. Tell me about the temperature of the sand. It's hot. Tell me about the temperature of the water. Pretty chilly. Pretty chilly. It's cool. Draw the convection current that's created during the day on the beach based on those relative temperatures. Go! And while you do that, I'm going to, those of you that just came in, Henry came in. Go up and draw it on the screen for me. Who wants to go up and draw it on the screen?
Yeah. It's up, yeah.
Really? Awesome. Yes. This is the convection current that goes with. So we know the air is rising over here, and when it reaches up here, it cools, and the air is sinking over the ocean. So how is the air blowing? It's blowing from where to where? From the water, aka the sea, to the land. Now here's the important thing about winds. Winds are like people. What state are y'all from? New York. What are we called if we're from New York? New Yorkers. Okay. Winds are named from where they come from, just like people. All right? Where is this wind coming from? The land or the sea? The sea. During the day, because the sand is so much hotter than the water, what kind of breeze do you get? This is called a sea breeze. You got it. You're sitting on your chair, the wind's blowing at you, nice and cool. Yeah? This is because of a daily change in convection currents because of the differences in temperature of the land and the water. Is that okay? All right. At night, you go back to the beach. What cooled down really fast? The sand. Why? Because it has a very low. You got it. Oh, you guys are rocking this. Okay. All right. But the water is still what? Relatively warmer than the sand. Okay, so now we got warm water, we got cool sands. Draw the convection current now at night. Okay? Middle of the night. Yeah, the middle of the night. They're the bioluminescent algae. Oh, I know what she did. She took bioluminescent algae and put it in a rock and tricked it. And one movie. Whoa, 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 whoa. Okay, real quick. Okay, so now the air is sinking over here. The air is rising over here. If we set up the convection current, what's happening? What is this? What is this breeze called? It's coming from the land. This is a land breeze. Got it? We're gonna watch a Ed puzzle on this tonight.